Hello, Jessitron.
Hello, Kent Beck.
I wish I had a cool nickname.
Your nickname is your whole name.
We have a system to talk about.
Yeah.
Not the system of nicknames. The system of airplanes.
Airplanes.
That almost rhymes. So speak to me, Jess, of the F-35.
Right. So there's this article about the F-35 recently that they finally admitted it's a failure. It's one of the slowest to admit failures. How many years has it been? It's decades.
Decades, for
sure.
Decades
that they've been building this plane that was supposed to be like a low cost replacement for the F-16s they're still
correct.
using. Because it is neither low cost nor a suitable replacement.
How does a disaster like that happen? In some normal linear fashion?
Never.
Oh, okay.
You can have linear failures, but disasters take a feedback loop.
That goes on a t-shirt, I think.
True. We need to make more t-shirts. We were like, there's a system in here somewhere. And the article mentioned it.
Yes.
The Forbes article mentioned that they had a plane and it was a little complicated, as planes are. Planes are complicated. And it was sufficiently complicated that introduced delays.
All right, so we have complexity.
Is that an F? I guess that's an F. That's a very pretty F.
Thank you. It's cursive.
All right, we have complexity, which leads to delays.
Delay.
Yeah, and we could talk a lot about why that is, but it is.
Correct. Yeah.
And then delay gave people time to come up with more things the plane should do.
Okay, so we have new requirements.
Yeah. At least, I mean, maybe at some point they were gonna release it, a more minimal one, but once some part got delayed, well, now the rest of us have time to do more work and we've got to keep busy.
And the Russians, or the Russians added this, or the Chinese added that, and now we have new requirements.
That's true, because as time passes, the standards go up. Right.
So it's legit. It's not like people were just making stuff up for fun. True.
It just really, as time goes by, you need more from an airplane. Correct. And of course, where do more requirements lead? Boom. Right back to complexity.
$1.5 trillion.
Trillion. Is that the cost of the program total so far?
I'm not sure about so far or projected, but in any case.
And how many useful airplanes do they have out of that?
How many times could we have gone to the moon with that? Yeah, exactly.
Oh my gosh. Well, and the other thing was that the complexity led to more than delay. It actually led to the planes not being useful.
Yes.
Because it's not just one plane anymore, right? This was supposed to be a low-cost airplane, but it has like right at the top of Wikipedia, it has like 3 modes, 3 main variants: the conventional takeoff and landing, the short takeoff and vertical landing, and the carrier-based. So like the 3 branches of the military need different things, and they decided to do all of this with one plane. And hint, when you say, let's do all of this with one X, there's nothing simple about that X.
Correct. Complexity leads to failure.
Right. But this feedback loop leads to disaster.
Correct. That's the only way you can spend $1.5 trillion is with a positive feedback loop just like this.
Yeah. Can you draw some disaster in the middle of that loop? Like maybe some fires, or that this is fine, dog.
You have much greater
Ooh, yeah, there we go.
That is the artist rendition of fire.
Excellent.
Do I need to label it as fire, or we got it?
It's okay. We verbally labeled it. People
Okay.
know what it is now.
All
But
right.
see, diagrams, they communicate really well to people who participated in their drawing, and everyone watching this has effectively participated in the drawing and therefore understands it.
Whining taxpayer, what would you do about this?
Oh, can you draw the whining taxpayer?
We are both,
Oh, that's just
that's
us.
us here on the side. What would you do to change this? We'd say anytime you have a positive feedback loop, you can drive it both ways. Hallelujah. So where would
Okay.
we intervene?
So when you have a positive feedback loop and you want to drive it the other way, you have to intervene at every point you possibly can.
Now, that's interesting. I always pick a place to start.
You pick just one? Well, I mean, you got to start somewhere. But I think you need to intervene at all of them. For instance, now as a taxpayer, I don't know, but if we could reduce requirements, if we could be like, okay, you want a cheap plane, you, just the Air Force, what do you need in a cheap plane? And remember, you wanted it cheap.
Yes, and we'll deliver it to you first. That's a reduction in complexity.
Reducing requirements reduces complexity. Programming is actually a total place where you can reduce complexity. First of all, as your requirements decrease, if you want to reduce complexity, delete code. Oh, the other thing that we can do in software, and engineers do with planes, is point out where if we tweak the requirements, we might be able to accomplish the same thing with less pain.
Yes.
That's a thing that we try to do in software, and sometimes you can do with real engineering projects too, right? So when you can reduce complexity, of course, do.
Wait,
and
real
that can be slower.
And you said real engineering projects as opposed to software.
Okay,
and
physical engineering projects.
I cannot let that go. It's a much longer conversation than will fit into this video, but that's fine.
I did actually mean real in terms of physical world, as opposed to virtual world in software.
Okay, it was
more of an IRL kind of real.
Got it. Fair enough.
Yeah, I do mean IRL engineering projects.
Okay. All right.
As opposed
Fair
to
enough.
software. Can we also reduce the delay?
This is okay. So here's where I'm gonna push back. I think it's tempting to want to just reduce the delay, but the delay is there because everybody's incentivized to delay. Cost plus contracts.
Really?
Sure.
Okay, great. So let's reduce that incentive.
Oh, we're just gonna overhaul Lockheed Martin's
okay. I mean, I'm not thinking about any of this as a taxpayer. Okay.
And
Step one, think big about a lot of things. Step two, look at those and be like, okay, which of these might we actually be able to come up with some way to influence?
Yes. So this is a big thing that we've looked at this.
If you start from, I don't know how to do that, then you're never going to do anything.
Sure. But I'm saying delay is not an effective place to intervene.
Well, look at continuous delivery. In software, delay is absolutely a place to intervene. I don't care if you don't have all the requirements met. Let's push it to production. Now,
yes,
okay, I don't know that works with airplanes.
Only once.
It totally works with software.
Yes, it does. Right. So there is a version of this where there's some delay, and you just get rid of it.
This is probably not true, but is there such a thing with airplanes? I mean, can you implement fewer features but fly the thing sooner? It's a lot easier with software than with airplanes, but it can happen.
But entirely doable. I went to a presentation by the guy who led the Gossamer Condor, the human-powered flight. Yeah. And they would do that. Their competitors had beautiful drawings, and they would just slap stuff together and try it out. If they had a problem, they would try and make it worse instead of trying to fix it. So they would take,
if it hurts, do it more.
Yeah, the example was they took a model. They had some aerodynamics problem. They took a model and they put it in the swimming pool and felt it.
Okay.
They used their arm to pull it along, and they're like, "Oh, that's the point at which it starts wiggling."
Nice.
Because water is a worse fluid to fly through than air is.
Oh, okay. So, make the problem worse because that gives you visibility a lot sooner.
In a safe way. This did not involve killing an endless succession of.
That's like chaos engineering.
Yes. Yes.
During the day, while everyone is there.
That's
if
right.
you think your software can withstand this, then try it.
This is a good system. It's such a simple system. And yet nobody got out of it.
But then you talk about the incentives of the companies doing it have incentive to make more delay. The branches of the military are like, if we don't get this now, we're never going to get it.
Never going to get it. That happens all the time in software development too.
Right. Which delays the tests because then, well, it's not valid unless it has. No, admit it. It's totally valid without whatever that sensor is, and you can add that incrementally.
Yeah, I was watching a documentary on World War II fighter planes, and what they said was the most successful planes were not the ones that were the best the first time they flew. The most successful planes were the ones that improved the most over the generations.
Reducing complexity is not reducing the work. It takes more work to find the elegant design. You don't do less work because you have an elegant design. You do a lot of work to find an elegant design, and after that, you're able to improve.
And then, and then you do less work. But getting into this learning loop in a concrete, specific way, looking back now, me knowing nothing about military procurement or aeronautics, I would have wanted them to get the first plane in the air as quickly as possible.
Yeah.
All the way to combat, all the way to actual, let's use this in the way it's intended to be used, and then we'll learn stuff about it. And that will go into the next generation.
And often you'll be like, okay, the next most important thing is definitely a seatbelt.
Right. Yeah, or bigger engines or whatever it is. All right.
Another that's system plenty about the plane.
Successfully mapped.
Okay. One aspect of one arbitrarily bounded system. Successfully. Sure. All that matters is that it led to more thoughts and ideas that we might not have thought of to do it better with the next replacement for the F-16 and then the next one.
Yes, which is what leads you to the B-52 still flying after 60 years. Well, thank you, Jess.
Thanks, Kent.